Hi, I'm Victor Maldonado, and here at Drone Developer we specialize in helping entrepreneurs and companies develop their own custom drones for specific applications that outperform the competition. Today we have a special topic. These are the design differentiators here at Drone Developer that sets us apart from any other consulting company out in the commercial UAV industry. So these design differentiators are based on many years of research in both aircraft design as well as flow control. So let's begin. So the first on the list is what we call reconfigurable and modular design techniques. And so when we talk about reconfigurable systems, some of you may be familiar with power tools. So in power tools, you have interchangeable heads that allow you to take the tool from, let's say, a drill to a recirculating saw. And so these tools allow you to achieve different tasks while using the same body as well as the battery. So this philosophy also applies in unmanned aircraft, although it is not common. It's still a research area. And so then for UAVs or drones, it allows you to essentially have a reconfigurable system where you can achieve different missions with different flight performance. So for example, low speed, high endurance, and high speed long range. And also for the capability of vertical takeoff and landing. So in this example, this image that you see here, you have an example of a fixed wing vehicle as well as a quadcopter vehicle. So you see that there's modules that are being shared. For example, the ducted rotors that are on top of the wing are reconfigured and put onto the sides of the fuselage body for the quadcopter configuration. And so that allows you to quickly interchange the modules at the field in order to perform missions that require vertical takeoff and landing or missions that require efficient forward flight. So this is a very useful example. I think that we will see these types of reconfigurable vehicles in drones in the industry. Let's get into the second one. Hybrid drones are fundamentally fixed-wing vehicles, but they use multiple rotors that allows them to accomplish the vertical takeoff and landing, either through a rotation of the rotors or a tilting of the body. So this leads me into the two main types of hybrid drones, or hybrid aircraft in general. So the first is the tilt rotor design that was made famous by the V-22 Osprey. So for these designs, you have the two rotors that are synchronized to move together during the transition sequence. Now, the tilt body design is actually the one that we prefer to work with. In this case, the entire body rotates by 90 degrees to go from hover to forward flight. And this happens through throttling of the forward and aft motors to create a pitching moment, right, which is going to transition the aircraft from hover to forward flight. So I would say that the tilt rotor design is complex. So I'll give you an example. So in the video that you see here, we tried essentially designing a mechanism that would allow transition for a hybrid vehicle. So these rotor arms that you see in the video would be placed on the wingtips of the UAV. And through the control functions, we're able to control the movement of each of these arms. However, you'll notice that in these two mechanisms, these are two separate mechanisms. In other words, there's no rod, there's no shaft that connects the arm from one side of the wing to the other. Okay, so it becomes very difficult. So what happens is that even though you send the same commands to the arms, okay, in this case, the rotation of the arm happens by throttling each of the two rotors, the one on the front, the one in the back. And by this differential thrust, you're able to produce a net torque that rotates the shaft of these two arms. However, they're not synchronized together just because there's variances in the way that these two systems are designed. And so you see different overshoots as well as different transient behavior that would make an aircraft kind of unstable. So if you were to apply these for a drone, it would make the transition sequence fairly unstable. And so that's why we prefer to work with tilt bodies, which are very simple. Just by throttling the motors, you can get a rotation of the body. So our third and final design differentiator is flow control. So flow control is a topic that is close to me because I obtained my PhD in this area of research back in 2012. So flow control works by manipulating the flow that is very close to the surface of the airfoil or the wing. And in most cases, you're going to want to delay flow separation. So this results in a decrease in the pressure drag, which essentially translates into less power that is required for forward flight, or less power that is needed to rotate a rotor. As you see in the example here that I'm showing, you see essentially a three-bladed helicopter rotor that has synthetic jets. And these jets, we've shown that if you activate them at the right frequencies, you can essentially manipulate the flow, the boundary layer, which is what we call it, and increase its momentum very close to the wall. And so as you do this, the flow is going to be less likely to separate because you have more momentum near the wall, which is where you need the energy. So the other form of passive control or flow control is actually passive, where you don't need any energy input. And so even though the active form of control can be feasible for UAVs, we actually prefer to work with passive technology. And the reason is because it requires no moving parts or energy input. And so it's a much cleaner technology where you're not, again, adding any energy input. You don't use much weight, right, in the form of devices or actuators. And so then active flow control and then passive flow control as well is something that is starting to be seen in aircraft. So you may be familiar with what we call vortex generators that occur, or rather they're placed on wings and they're used during takeoff to increase the lift coefficient and delay separation. So there's similar forms that can be used right on drones. So I've actually been working with a company called FlowRadar that specializes in designing these organized microstructures that are put on the surface of the airfoil or the wing. And so they delay flow separation, and these can be used to increase the range or endurance of a drone by about 10 to 15%. For more information about our design differentiators and to learn about how we can help you, please visit our website at dronedeveloper.org, or you can email me at victor@dronedeveloper.org. You can also find our information in the description below. Stay tuned in the coming weeks as we're going to be getting an exciting series on the conceptual design process, and by extension for drone design. Thanks again for watching, and we'll see you again next time.